Hello, friends. Welcome to the Georgia Tech AI podcast. My guest today is Jeremy Collins, a machine learning PhD student advised by Animesh Garg. His research primarily focuses on the intersection of deep learning and robotics. He covers topics like video understanding, visual motor control, and scaling robotics for real-world deployments. This conversation was an absolute joy for me. He's tackling some of the pressing problems in robotics, like how robots need a tremendous amount of data to learn even simple tasks, and their inability to generalize to different domains. He's also unafraid to ask some of the important questions about research, about our mortality, and consciousness. I'd now like to end with a few words by Ginny Rometty. The key to success with AI is not just having the right data. It's about asking the right questions. What are some aspects about humans that amaze you and it's really hard to replicate in robots?
Wow, yes. Humans are so amazing. Okay, let me think. I'll start with this. I think the most beautiful fact about the universe is that there's something here, part of the universe, that's able to observe itself. And the only beings that we know of that are capable of this are humans. So there's some special sauce there where we're able to sort of recognize our own cognition and recognize really the beauty of physics and the system that we lie within, still trying to discover new stuff. But yeah, I think that's the special thing, this sort of self-awareness thing, whatever that is.
Understanding how the world works, it's complicated because a lot of people say robots don't really have an understanding of the world, that it's rather superficial. Do you agree with that?
Sure. I think there's a lot of baggage in the word understanding. Lots of times people kind of talk through each other and don't have the same definition. But the way I define understanding is from like two perspectives. One is that you can approach a concept from multiple angles and explain it. And then the second thing is you can sort of derive it from first principles. I think robots are capable of that to some extent. Of course, they still make mistakes, although humans also make mistakes. So it's a bit of a fuzzy boundary between sort of memorization and understanding. So I'll say robots can understand to some extent, but humans can also understand to some extent.
There's How much of intelligence do you think is statistics?
You could argue everything's statistics. If you visualize every point in space, all of the fields, like the electron field and what have you, those are all just numbers evolving over time, and it's probabilistic too. So you could call all of physics statistics too. That's fine, right?
That's true. But statistics doesn't model causality. I think understanding causality is so critical to any kind of system understanding.
Yeah, I'll push back a little bit. I think you can model causality if you have sort of a sequence of conditional probabilities. There's this thing which we might get into called a counterfactual, which means you change one of the conditional variables and you see if the outcome of some process will change. I would call that sort of causality.
I see. Yeah, so let's get into it. Your recent work was RoCoDA, and it primarily dealt with data augmentation. Can you talk about this whole concept of counterfactual data augmentation? What is that?
Sure. Yeah, so RoCoDA is a way to expand the size of a robotic data set. One key bottleneck I see in robotics is the amount of data that we have. Typically, the way this works is you'll have people operate the robot, sort of remotely control it with an Xbox controller or something, and you'll record the data with the goal of modeling the behavior that the human invokes on the robot. But the problem is this is quite expensive and time-consuming to collect this data. So to address the problem with RoCoDA, what we do is we leverage symmetries in this data. In particular, we sort of use this, what's called causal invariance, which is just a fancy way of saying we determine what parts of the environment are relevant to the task and which parts are irrelevant to the task, or more specifically, the robot's actions. And so how that works out in practice is we can randomly perturb some parts of the environment, particularly the parts that don't change the action, the correct action. So if I'm trying to grasp an object, say a cube, like a child's block, I could move background objects however I want to, as long as they're not in the way of the robot. Yeah, so that's sort of the key idea behind how we're able to artificially expand the size of the data set, is we just move these objects around that don't really matter to the robot.
How does it differ from what came before in terms of
Yeah.
data augmentation and counterfactuals?
Sure. Yeah, I think the key difference here is interaction with the environment. Typically, people augment data by changing how the images look to the robot. So you can do some things like changing the color or cropping the image differently, that kind of thing. But while those are still useful and actually part of our sort of data augmentation framework for RoCoDA, there's more you can do. And you sort of get diminishing returns on these things. So you may only get like a limited return, even if you were to, say, expand the data set by 1x. You don't get 1x the performance. It's more like a logarithmic sort of relationship.
Yeah, I wonder how you focus on the things that actually matter in your observation space. That this is particularly relevant to the task and this is irrelevant. How does that partitioning happen?
Yeah, right now I would say this is our biggest sort of hack for the method. Right now, humans have to specify this per task. So we only have a set of, I think, 5 tasks for this work. So it's really not much work to annotate these things. But for version 2 of this, our goal is to exactly discover this causal structure. One way you can imagine doing this is by training what's called a dynamics model, which is just a way to predict the future. So you can have the same sort of remote controlled robot data set, and you could predict the frame at time t+1, given the frame, the camera frame at time t. And why that's useful for finding causal structure is you can ask the question, to predict the state of each object at the next time step, what did I need to pay attention to? So what's cool about transformers is that they can pay attention, and we can figure out by looking at the guts of the model, we can figure out what the model is attending to make a prediction. Yeah.
How does it get harder when the system gets more complex? There are more inputs. There's also that risk of mistaking a correlation for a causation.
Yes, exactly. Yeah, first let me talk about correlation versus causation. Maybe that's necessary for understanding this causality stuff. So you may have heard this, correlation versus causation. There's quite a difference. So if you're observing a data set without interacting with it, you may observe that certain events occur together. One example that I like is the wind blowing and trees swaying in the wind. These things almost always occur together. And the funny thing is, if you're just observing that data, say you have like one number for tree swaying magnitude and one number for wind speed, these things vary together. If you train a machine learning model on this data, it might mistakenly think, oh, if you sway the trees, the wind will start blowing, because of course they're very correlated. But to sort of break that mistaken viewpoint, you could actually ask what's called a counterfactual question, which we alluded to earlier. And in this case, the counterfactual question would be, if I went up to maybe a small sapling and I shook it, would the wind start blowing? And the answer is, of course, no. But this is that sort of counterfactual question that we're asking with RoCoDA. The analogy here is, if I change the object state of something that's irrelevant, does the action that the robot needs to take change it? And so let me get back to your actual question now.
Yeah.
Your question was, as the tasks get more complicated, how does this change this relationship? What changes is you find more what's called spurious correlations in the data set, the more inputs that you give the model. And the way that the typical models work that just fit the actions directly, like I said before, where you remotely control the robot and then try and copy the actions down, they typically overfit to the data set. And this actually works in practice as long as you don't change the environment. But they will latch onto these sort of spurious correlations, which again is just a way to say that as different aspects of the environment change, we don't know whether that's a causative part of the environment or whether it's just a happenstance, like sort of coincidence that these things vary together. But RoCoDA actually benefits more from these complex situations because there are more combinations of the relevant objects that you can change. And so that essentially increases the multiplier on your data set size as you augment the data.
That's a really strong point because, when you look at humans, as systems get more complex, it almost gets more difficult for us to infer causality, especially in a complex system, because there's only so much we humans can observe. And when you're operating on limited data, sometimes you might take a few extra liberties and draw a causality link that doesn't really exist.
Yeah, humans do this all the time. One example could be superstitions. You walk under a ladder, or you see a black cat, that kind of thing. You could call those spurious correlations. If you see the black cat cross the road and then you get in a car accident or something, one might draw that correlation, even whether or not it exists.
Right. Yesterday when I was prepping for this interview, I was thinking about the butterfly effect, where a butterfly flaps its wings and it
Yeah.
causes a hurricane somewhere else. I
Mhm.
really wonder if, an AI system could one day detect, okay, this assassination could lead to this world war. I wonder if it would be possible to draw those kinds of connections.
Maybe. I do think we live in a chaotic system, I would say, and that's kind of what enables the butterfly effect. I think it's possible. I do think not to get too technical, but I think the complexity on this is kind of like exponential. So there are exponentially many ways that this thing could diverge, and so it may take more and more compute to sort of plan further out. But it's probably possible.
Even causality does change. Sometimes the reason for something happening actually might change over time. There's a dynamic element at play.
Yeah, you could have the same outcome, but two different causes. Yeah, absolutely.
Let's dig deep into some of your other work. I feel a lot of this centers around the theme of generalization and making sure that robots can adapt themselves to different environments. You had a paper called AMPLIFY that you shared with me. What is the key goal here?
Right. This work has almost the same motive as RoCoDA does, and that's sort of alleviating the data bottleneck in robotics. So typically, we can only leverage this sort of expensive direct robot annotated data, like I alluded to before. We call that demonstration data. What AMPLIFY does is it relaxes this assumption and explores how we can use different sources of data. One being videos of humans or videos of robots acting in the world with no action annotations. So we're not tracking hand pose or anything like that. We're instead just observing motion in pixel space. And then the second source of data is what we call off-task data, which is essentially the same as demonstration data, except there's no specified goal for the robot to achieve. So this could be robotics data on a task that you're not actually going to be testing on. So it could be a different embodiment, or it could just be also what's called play data, which is just acting in the environment in reasonable ways with no given goal. So what AMPLIFY does is it leverages these two types of data in order to, again, expand the size of the data set. But the methodology here is different. The way that we leverage these sort of three sources of data, so we also have demo data, that's the third source. The way we leverage this is by breaking down what's called behavioral cloning into multiple modules. The first module is a forward dynamics model, which predicts the future observations conditioned on language. So you can imagine this sort of like video prediction, except we do something slightly more, I'd say, efficient. And then the second stage is called inverse dynamics, where given the next state predictions from the forward dynamics model, we predict what actions would be needed to cause those states to happen. Yeah, so that's the high level of it. There's more detail we go into with how we capture states in motion and that kind of thing. That's it.
So what you're saying is you're pretty much eliminating the need for any kind of action labeling on data sets. I could feed thousands of videos to a robot, YouTube videos, and it could learn juggling, for example.
Yeah, in principle, it could, although there's one caveat. So for the inverse dynamics model, we do need action annotations because the goal of this thing is to sort of map evolution of the environment to the actions needed to create that change in the environment. But what's nice is we need a lot less action annotated information than you would otherwise need. And we show this in our results. The thing I'm most proud of from this paper is we're able to execute tasks that we don't have any action annotations for that specific task. So we have some action annotations, but they're for other tasks. So you call this a task generalization. And to my knowledge, we haven't seen anyone else do this for the particular benchmark that we were training.
What kind of tasks, by the way?
Yeah, so most of the tasks here, so I'll say the benchmark is called Libero. It's a set of 130 different tasks. Most of them end up being pick and place, which is kind of typical of robotics. But there are some more interesting tasks there too, such as turning an oven knob, opening a drawer, putting a book in a shelf, sort of like more precise than just pick and place. Things like that, yeah.
Pick and place is not trivial. People think pick and place is really easy, but I'm sure you would agree that's pretty much 90% of the tasks involved in robotics.
Yes, and it's not a solved problem. Many people have claimed it's solved. Yeah, there's a lot of complication to it once you start trying to make it like a task-oriented grasp or task-oriented placement.
What is this conversation around long tails in terms of a lot of actions are context dependent and they can get complicated really soon. Even a pick and place task, it really depends on where you are, what you're doing. Can
Yeah.
you talk more about that?
Absolutely. So one could claim, like, I feel like the way a lot of people think about robotics is how hard could it be? You just go up to the object, you close the gripper, you go to the target location, and you're done. And I'll agree to some extent, you can do that to solve a lot of problems. But like you alluded to, there's this whole long tail problem where the majority of tasks are actually quite rare. Not the majority, but the majority of effort will go into tasks that are quite rare. And you can draw the analogy here to autonomous driving. The analogous question here is, how hard could it be? You just have to follow the lanes. If you cross over the left lane, you turn right, and vice versa. And sure, you can solve this problem. Like one grad student in a week could probably make a lane following algorithm. But you run into these edge cases all the time. What happens if a trash can falls over on the street and you have trash everywhere? You need to avoid the sharp bits and hit the soft bits. And similarly for robotics, what happens when you're doing the dishes and you drop the plate and it shatters everywhere? Do you grab the broom? Do you tell your owner or the human what happened? There are all these edge cases. And even for grasping, something as simple as grasping, you don't want to grasp in the wrong place. Say I'm grasping a water bottle, but the lid is off. I probably don't want to grasp it by the lid. And there are constraints now. I don't want to turn the bottle 90 degrees. Yeah, that's one example. But it's a very tough problem. And I think it's going to take a lot of effort to solve.
Do you intend on solving it? What are some steps that we can take?
Yeah, I mean, I want to contribute to the solution for this. The most direct thing to do is to scale up the data, but the counterpoint to that argument would be this has not worked necessarily, or the problem's not solved for autonomous driving. I like drawing the analogy here because it's sort of like the same paradigm as robotics, but pushed further ahead in time. Yeah, so I think more data is part of the solution here. I'm also quite bullish on reasoning, and that we need to, in my opinion, sort of start interpolating between low-level actions and high-level language. Language models are quite capable of robustly solving problems nowadays, at least in the realms of like math and coding. And I think they could do something similar when it comes to robotics. Like I would say, if you tell ChatGPT or DeepSeek or whatever, if you tell it, I dropped the plate, what do I do now? It'll come up with pretty reasonable solutions, 3 or 4, one of which is probably correct, like sweep the floor or what have you. And I think if you connect this to these sort of behavioral cloning models, which learn how to predict actions given observations, I think that'll give you the robustness, or at least this is part of the solution, to sort of generalize to these unseen situations.
Okay. Yeah. I want to get back to AMPLIFY now. Thank you for indulging me with this
Of course.
tangent. But what is an actionless motion prior?
Yeah, great. So let's get into the nitty gritty. So the way that we predict future states for the 4 dynamics model that I talked about is we actually track locations in the image and we predict where they're going to move in the future. So what we call this actionless motion prior is a way of compressing the actions into a discrete latent space, similarly to your vocabulary for a language model. You only have like 100,000, 200,000 words that you can choose between. In the same way, we break down motion in the video into a set of discrete tokens that we can auto-regressively predict, very similarly to a large language model. So in order to learn these tokens, we use what's called a variational autoencoder, which is just a way to compress and then decompress these sort of key point trajectories. Yeah, so that's how we learn the tokens. Once you learn them, you predict the future locations of all the points. I should specify we have this 20 by 20 grid points in the video. Each of those points, for the next second or so, we predict where the point's going to move given the task. Yeah.
What is the key point trajectory?
Great. Yeah. So I should be more specific here. So a key point, we can say, is just a location in the first frame of a video. Okay. So we can specify, x equals 100, y equals 252, whatever. And there are these nice off-the-shelf point tracking algorithms that we use to get our ground truth. And by point tracking algorithm, I mean you give it the same initial points, but you also give it the entire video, the entire feature, and you track the points as they go through space. And what's really nice is that there's some recent models that have been released. The one we use is called CoTracker, and it's quite robust. It can deal with occlusion, so if your point moves behind an object, then it'll continue to track it. And if you move the camera around, it's quite robust to this.
So how does all of this translate into understanding what the action was and how to perform it?
Right. Yeah. So our key intuition behind using these key point trajectories is we think they encode a lot of action information. You can ask, what is an action? Typically in robotics, we parameterize actions by delta gripper pose. So how does the translation and rotation of a gripper change from time step t to time step t plus 1? Our intuition behind using these key point trajectories is you have enough information in these like pixel trajectories, these key point trajectories, to unambiguously predict the action that corresponds to those trajectories. And that intuition turned out to be quite true.
A lot of this is a prediction problem. We're trying to understand how actions evolve over time. Say that I masked a certain part of a video and then asked Amplify to fill in the gaps. Could it infer what the missing actions were?
It could if we trained it to do so. You could argue we're doing this in some sense by masking the future and then predicting the next step. There's another way to do this called masked autoencoding, which instead of doing what's called causal masking, which is masking always forward in time, you can mask any time step and fill the prediction. And that is actually a more general way to approach this. I would say the ceiling of performance might be higher, but it would take more data to learn this.
You mentioned that we're operating in pixel space. Say that I also want an understanding of the spatial elements at play. There's an element of wanting to account for three-dimensional
Yes.
spaces. Is that something that Amplify is doing right now?
I would say it's not directly doing this. One way that we do get 3D information, though, is by using multiple views from the camera. So when we test this thing in the real world, we actually use 3 different cameras and predict the motion in all 3 perspectives. So you could say implicitly you do get 3D in the same way that I have 2 eyes and I can still see 3D, even though if I close one eye, I only see 2D pixels, right? But I think in the future, we want to have a more explicit representation of the motion in the video. Mm-hmm. The bottleneck with that right now is actually the point tracking. We've tried some 3D tracking methods, but the depth dimension is quite noisy. So you end up kind of predicting the noise rather than the signal in the depth motion, the depth direction of the motion.
I see. So you almost have to solve this problem with more data, with different viewpoints, so that you can build one particular model of how this action transpires over time.
Mm-hmm. Yeah, I'd say so. One missing element with this, if we were to continue doing multi-view 2D, is having correspondence, which just means we want to have the same 3D points being observed in both camera perspectives. Like I said, we just have this 20 by 20 grid of points right now, but you can imagine we pick task relevant objects only, and maybe we randomize the rest of the objects, like in RoCoDA. Yeah.
How could something like this be scaled to the real world? I can see a lot of promise in training robots with videos. And maybe I have a robot at home and I can train my robot as well to perform some specialized task that I wanted to. Is this a possibility? And what are some challenges that you think might come up?
Yes, it's a possibility if you're patient. I think this is absolutely going to happen, but sort of my hot take is that robotics will be the last domino to fall when it comes to applications of AI. And first, we'll have all of these cognitive tasks being solved first, which is kind of backwards to what people's intuitions were with, say, the Jetsons style thing, where you have robots, you have Rosie the robot, all of that stuff first. But no, the real world becomes quite hard. There's this thing called Murphy's Law, where everything that can go wrong does go wrong. And I observed this quite recently doing some real robot experiments for AMPLIFY. There are so many things that can go wrong. Like if you accidentally bump the camera, the pose slightly changes. We weren't trying to generalize to different camera poses. You also have an issue called compounding error, where if your robot makes a slight mistake in its action, you'll see an observation that's not been seen before, which makes it take a worse action. And then the issue compounds. We also had some issues with the background changing. We had a table up behind one of the cameras for one of the tasks, and we forgot to put the table back up at some point, and the policy wasn't working. And so just lots of small things like that. The way I think about this is it's like balancing an inverted pendulum. It's kind of a chaotic system like we talked about earlier. And every little piece in tandem has to go correctly for the thing to work. So it's very hard. You asked about personalization. I think that's going to happen too. And the tools are starting to come in place for this. You can have personalized models by including your history and, say, the context, just like you would for ChatGPT. You can give it, sort of your memories, and it can look them up. You can also train models very efficiently these days with something called LoRa. You can train very few parameters to sort of update the model. Yeah, there's lots of stuff here. And I think the way this would need to work is it would need to observe your daily habits and sort of understand what your wants and needs are and understand your sort of personality. So that's another thing that's sort of needed.
Hardware is such a big issue. I mean, even in this past decade, there's rarely been a robotics company that has survived. It's easier to dominate in the software space, but hardware can easily break. And how do you solve a problem like this? Because you mentioned that robotics is the last domino to fall, but it's a heavy domino. It's going to take a while. Really, I'm curious, how can we make these systems more robust to all the volatility that can occur in the real world?
Yeah, I really think this is an unsolved problem at this current stage. But you bring up another of the key bottlenecks here, which is hardware is going to break. And if each household has its own robot, what do we do when it breaks? Do we have the owner fix it somehow? Do we have a maintenance or a technician come in to fix this? That's very expensive. It seems like the more sustainable solution would be to have a just very robust hardware system. But right now, there are not sufficient sort of market pressures for this, I don't think. Right now, robotics, or say like humanoid robots or mobile robots, are only available at the research level. There are some robot dogs that are more commercially available these days, but for the most part, the market is the research market, and there's a lot of incentive to not necessarily make them as robust as is needed for deployment in households.
Yeah, that there is a gap. I feel what's happening in research and actually productizing this so that it's useful in our day-to-day lives. I think that is a problem that's not being focused on that much because it is such a hard problem.
Yeah, and I also faced this with an internship a couple of years ago, where it was like a warehouse robotics company. And the problem at first glance seems pretty simple. You just have to grab envelopes and put them in the right bins. But there are always so many sort of fires to put out. And our clients would give us calls every couple of days saying something new is broken, like the lock to the door to prevent humans from being in the workspace of the robot. It broke. We need to fix it. Or the robot was handling a magnetic package and it stuck onto the stainless steel slide that leads to the bin. Lots of edge cases like this, and it's hard to account for all of them. This is exactly the long tail problem again.
I wish there could be a situation where the robot learns to fix itself. We don't have to worry about this. I feel that's such a great part of being an intelligent human being. You're facing a problem, you solve it. Say
Yeah.
your health is suffering, you change your diet, you exercise. But with robots, we're still not there yet. And I would love to see self corrective measures in place.
Yeah, absolutely. That's a really good point. Maybe once you have a humanoid robot or something that's generally capable, it can sort of apply its own band-aids per se, or go to the hardware store and buy its own replacement parts, or order on Amazon maybe. Totally. That's a really good idea.
I want to talk about, just research in general on robot learning and AI. There's a risk. A lot of people tend to focus on the same problems and also the same ways of tackling these problems. How is this something you avoid in your day to day? Intellectual monoculture, there's homogenous opinions everywhere. How do you ensure that you have your own perspectives and you're thinking for yourself?
Yeah, I would say this is where my background kind of comes in a little bit more. So I got my bachelor's degree in mechanical engineering, actually, not in robotics or not in AI. And I think this helps me sort of go against the grain to some extent. I think a lot of the source of this sort of monoculture is through social media. I'll hear some of my AI friends talking about the same papers at the same time or the same talking points at the same time. I think a good way to avoid this is to try and not have a recency bias as much. And so this could come in the form of reading books from people, decades ago, or from actually listening to podcasts. Part of what got me interested in AI in the first place was listening to AI podcasts. Yeah, so I think just sort of zooming out and realizing there's a whole history of thinkers and ideas around, and it's not just the past week of AI papers or people trying to get engagement on Twitter or whatever.
It's a real danger because sometimes you forget why you're in the field in the first place. Is it about getting X number of citations, or is it about chasing a real important question that you're passionate about? So I want to ask you, what are the motivating questions for you as you pursue robotics research?
Yeah, great question. So I think the biggest thing driving me right now is I want to impact people's lives, and the next sort of industrial revolution is absolutely going to involve AI. And my ultimate goal is to create a future where everyone can live their most happy and long fulfilling possible existence. And however I can make that happen, I think is what I will try and do. I think robotics is one key way to do this. One, because we're early to the party, things are not solved. It's quite a hard problem. And two, I think this is one of the main ways we can give people more free time to do what they enjoy. One thing that really, I think, is one of the most biggest tragedies today is that a lot of people don't enjoy their day-to-day jobs to the extent that they have their work and they have their life. They're both your life, right? Your work is half of your waking life. And I want to make sure that people enjoy whatever they do. So giving them the opportunity to do so by selectively automating fields that people don't enjoy as much, I think is the right way to do this.
How does this realization come in? You seem really passionate about what you do. I want to ask you, what gives you meaning in your day-to-day research? What are some moments that give you a lot of joy?
I think the thing that gives me the most joy is satiating curiosity, whether it's learning a weird technical quirk of an ML model or whether it's answering one of the big research questions that I had in mind. So I think that's the biggest driver for me, aside from making an impact on the world in my day-to-day, really just learning. I love learning. That's why I'm doing my PhD. And being around such great researchers at Georgia Tech, I think, is such a good way to do this. And it's an efficient way to learn. I learn all the time from my lab mates, from my advisor, from other professors. Yeah, I feel so grateful to be here today. Yeah.
How do you incorporate discomfort? See, I mean, it's hard showing up every day. I totally get you. Learning is so critical, and even I enjoy learning. Staying in the game, you've been in academia for 8 years now. You've been researching, you've been doing school. What How do you ensure that you're consistent and you stay disciplined towards your goals?
That's a good question. I don't know if I have the best answer here. I think a lot of this is aligning one's long-term goals with one's day-to-day. So just making sure there's not a disconnect. But like one thing, again, I'm just so grateful that I am able to tackle the questions I'm most passionate about. If it weren't the case that I were working in robotics, I don't know if I'd have the same motivation, right? So I think that's the biggest thing. You mentioned to some, I think you alluded to the concept of suffering here. I have a bit of another hot take on this. I think suffering is good to some extent in that it allows you to experience the peaks and troughs of life. If you just optimize for short-term happiness, I think that is at the cost of long-term happiness. I think if you think about this numerically, you kind of like saturate your happiness meter if you always go for the short-term happiness. But I think the average happiness in the long term is better if you experience the peaks and troughs.
What got you this realization? Is this something you experienced directly, that if I suffer right now, I will do really well in the future?
No, it wasn't that direct. I think a lot of this was through just listening to people talk and then reading some books about philosophy. Um, let's see. Someone who comes to mind here is Sam Harris. He was a big influence on me, kind of got me into meditating. I think meditation is one thing that allows you to embrace suffering as the raw signal that it is in your brain. Yeah, I don't know. I think it's a combination of that and then just kind of discovering. So combination of inputs from others and then just kind of exploring for myself what works and what doesn't.
Would it be helpful if we program suffering, discomfort into robots?
I think so, as long as it's not enough suffering to turn them against us. I say that half-heartedly, joking. I think suffering is good for robots if it involves making them more robust. So I think the same thing applies to humans. Suffering might allow robots to plan longer term, because if you kind of break down the concept of suffering, I think it comes down to two things. I think suffering is the experience of frustration, i.e., barriers to your goals. And then I think another component of that is physical threats, so avoiding death most directly. These are good qualities for robots to have. You want robots to be able to work around obstacles, whether physical or conceptual obstacles. And I think you want them to avoid hurting themselves. So suffering is actually a good mechanism to solve both of those things.
At least reflecting on life experience in general, the harder the goal and the more discomfort you experience in the moment, it almost feels better in the end when you finally achieve your goal. I think that's such a big drive. If there wasn't any discomfort, if it was easy, it wouldn't feel great. It wouldn't feel great in the end. It wouldn't feel worth it.
Exactly. This is a key component of fulfillment in my mind. It's not fulfillment if there's no trough in the middle of the process. Totally agree.
How do you think about death? The fact that we all have limited time. And I feel death is such a great motivator. At least for me, the fact that our time here is finite gives me a sense of drive that I don't want to waste any single day. I wonder, does that apply to you as well? Do you fear it or are you trying to work against it?
I'll say I do fear death, and I don't ever want to die. I want to be immortal. And one might say in response, doesn't death give you meaning? If you had an infinite life, there's no reason to do anything now. My response to that response is humans have a finite context and a finite sort of prediction horizon. So both ways, we're not able to conceptualize infinity. And I think in practice, what that means is you can actually plan out that far. The only things influencing your actions should be those things that you can conceptualize. And like one instantiation of this might be if I know I'll never die somehow, but I can't plan more than like a month ahead, or in research, I can't plan more than a week ahead. Then what interaction does that have? Actually, there's really no interaction between my actions at this given moment and the infinite horizon case. And in the same way, you might, if we talk about history now, you might say, oh, once you get bored, you'll experience every possible experience. And then I would say, oh, I only have a finite memory, at least before you augment my brain with whatever AI stuff. I only have a finite memory. And so by the time I've experienced every possible experience, I'll probably forget a lot of those things. Yeah, and then there's a whole line of thinking we could go into with you can modify your own goals at some point if you live long enough to experience like brain computer interfaces, that kind of thing.
Yeah, I would love to get into this. What is it about, our bodies and human immortality and how you could distinguish it from digital immortality? If I uploaded my brain onto the cloud, how would that be different compared to this body and how I am today?
Yeah, I think there could be no difference essentially. Um, Although the first question you asked me here was about consciousness essentially and self-awareness. Um, One thing I think that will always be special about humans to me is that I can be very confident that they're conscious in a very similar way to me because they're very physically similar. Our brains are 99.9% the same structurally. Maybe our neuronal connections are slightly different, but the overall structure is kind of the same. I can't say the same of a computer. I can't say the same of weights of a neural network necessarily. So that's what's special about humans, although I'm fairly confident that you can get the same structures that create consciousness in a silicon instead of carbon-based life.
Yeah. But it's hard to verify. That's the key issue, right?
Yes,
You don't
yes.
want to take that risk.
Yeah, people often break down consciousness into two parts. There's the easy part, the easy problem, and the hard problem. The easy problem is that of self-awareness, where I think my favorite way I've heard it put is by this guy, Wojciech Zaremba from OpenAI. His claim is intelligence is compression. And if you compress hard enough, the compressor will eventually be compressed as well. And that comes in the form of creating a concept of self. So if you call me the compressor, the thing that takes in raw sensory input and turns it into concepts in my brain, eventually I'll become one of those concepts because it's more efficient to model that, to predict the future or to not die. Anyway, this is the easy problem of consciousness. I say this is a relative scale. It's probably not easy on its own. But then you have the hard problem of consciousness, which is, what is that feeling you feel when you see the color red or when you taste the taste of vanilla ice cream? What is that? It's hard to communicate, but I would hope we all experience it. So people often call those feelings the concept of qualia, which is sort of the unit of sensory sensation, of like a subjective experience. Although one sort of controversial opinion I have is that consciousness is just a social construct. And this concept of qualia only exists at the level of a neuron firing in your head. This doesn't actually exist objectively, just in my own experience at the time. And one book that influenced me on this was, I read this a couple of months ago. It's called For Bacteria to Bach and Back by Daniel Dennett. What I like about his claim is it sort of unravels this whole, I would say, story around consciousness. And it says your only support for the claim of consciousness is the vehemence of your claim. So I can only really give you evidence that I'm conscious by how confident I am that I see the color red or I imagine the taste of vanilla ice cream. And there's no real way to verify beyond my convincing you of that.
Yeah. And so much of this is also based on this theme of attachment. This concept of self that we were so attached to. Do you feel there's a there's a there's a difference, the line that we can draw between discomfort, suffering, and unnecessary attachment to our bodies, to our identity, the self, because all of it keeps changing. How do we ensure that we live more in alignment with reality that keeps changing?
Yeah. That's an excellent question you're asking. So the concept of self, I see it as pretty related to that of consciousness. It's essentially the belief that we're persistent in time and that there's some distinction between the inside and the outside world. Um, but yeah, I think about this in a similar way to consciousness, in that it's a useful story to tell. But there's no objective truth to this, in my opinion. It's instead, the analogy I really like is we're essentially like language models predicting the future states, but we have this context, which is our history. And so, of course, what I say in the next moment is largely influenced by my history. There's no objective concept saying this is the thing that's you. It's instead, I'm made up of a bunch of particles acting in accordance with physical laws. Maybe that's a really kind of cold, calculating way to put it, but I think if we want to be objective, that's kind of true. But all that being said, I think the concept of self is extremely useful and necessary to operate socially. Like it's hard for me. I've probably said the word I and me 100 times during our conversation, and if I didn't, it would be kind of a weird conversation, right? I would say be talking in the third person all the time. Doesn't quite make sense.
Yeah.
So it's all kind of philosophical, but at the end of the day, it's more practical to think of things in terms of self.
Yeah. This can turn into a bit of a rabbit hole in terms of of philosophical discussions that we're having. But a very unuseful aspect of the self is the ego. Sometimes that can work against you and also close you to different kinds of thinking. How do you prevent this from happening? How do you remain open minded in your research and always willing to take in different inputs and not getting too latched on to certain ideas?
Yeah, I think a lot of what you're speaking to when you say ego is emotional attachment to ideas or biases that don't necessarily agree with experimental results. Say sometimes in research we get this bias toward our own work and saying like having this kind of narrow lens that we look at things through. And I think the best way to sort of counter that is um, try and separate yourself emotionally from those ideas. It's very good to be attached and from a motivation sense, but say when brainstorming, of course everyone says this, but there are no dumb ideas. There's no sense in filtering initially based on your biases. You just kind of have a bunch of ideas and then you filter in a second stage. Um, yeah, I think being flexible, being open minded, are quite important for research because a lot of times the most groundbreaking works break some core assumptions, and the way that's done is by detaching oneself from the ideas that one has done in the past. This is another sort of like recency bias thing, I would say. So, previously I worked on those two works, RoCoDA and AMPLIFY. For my next thing, maybe it doesn't involve these. I'm open to that idea.
Yeah, robots have an advantage because maybe there could be a day when we can see our own biases in broad daylight and we finally understand my thinking is really colored by certain facts that I hold dear to me that might not actually be true in the first place. And maybe robots could reveal that about us and we can learn about ourselves through them. Is that something you think about?
Yeah, I've observed this a little bit. If you've seen, I don't know if you've seen, ChatGPT has like memories now. This GPT 4.0 has memories where you type stuff in the prompts, and then sometimes if you give it permission, it'll remember stuff about you. I don't remember what it said in response, but I asked it, "What's a surprising fact about me that I would not have thought of?" And it had a pretty deep response. It's pretty cool at, pretty good at objectively viewing your actions and viewing your opinions in a way that in a way that's not as easy to do from the inside. It's good to have this sort of third person perspective. So it's almost like a therapist, I would say.
A cheap therapist, it's not
Yeah,
even that expensive.
yeah, for sure.
I want to close this conversation with some of the advice that you have for budding researchers in AI and robotics. My first question is around building systems, building routines, building habits that have served you really well over the course of your academic and research career.
Okay, yeah. So, I would say try and build habits with the long-term goals in mind. One sort of moment that comes to mind in my head is when I'm about to leave the lab and go home. I always go through this thought: what do I value more? What I will do when I go home, or what I'm doing now? A lot of times, the thing that motivates me is having the realization I value what I'm doing right now, like at the keyboard, more than going home and just being on my phone or whatever. Just having all this is to say, have the long term goal in mind. This again is very relevant to aligning your incentives between the short term and the long term. Um, yeah, as for other habits, I would say try and absorb as much as you can. Follow your curiosity, though. Don't force yourself to learn about what you're not interested in. For sure, follow your passions. The way this happens for me is I watch a lot of YouTube and listen to a lot of podcasts about AI and about robotics. So that's another thing. And if you're looking to learn more about AI and machine learning stuff, I actually have a doc. Maybe if you could send a
I
link
will share
to
it in the
those.
description. Yeah.
Great. Yeah, I have some of my favorite machine learning resources in there, as well as some of my favorite podcasters and YouTube channels, and I think Twitter handles as well. So, in my opinion, that's a great way to get started and deep learning and machine learning for robotics. Yeah, that's what I would say. And then robotics is quite interdisciplinary, so there's a lot of flexibility in following your passion. Maybe your passion lies more on the mechanical side or the electrical side or in computer science. Whichever of those things it is, I'd say follow that. Don't force yourself to jump on the AI hype train if you don't feel passionate about it, because it's much more motivating to follow what your interests are.
Yeah. And for the listeners, I want to push back on the advice of follow your passion because in your case, if I look at your story, it's not as if you started day one with AI is the thing that I love. You cultivated that passion with a lot of work, research, but you also watched podcasts. You opened up your mind to different subjects. And I feel that is what just rekindled a lot of passion for different things. And now you are who you are.
Yes, you're absolutely right. And I should speak to that too. One way to frame this is through exploration versus exploitation. Exploitation would be following directly. I think I know what I want right now, and I only follow that. But there's a lot of value in exploring and trying new things that you're not sure whether you're passionate about. And this is what happened to me in around 2020. I started listening to the Lex Friedman podcast and listening to people who were very passionate about AI. And I realized this is very interesting and it's absolutely the future. So I want to explore that and see if it's something I want to work on. And I would say I wasn't sure about that passion until I actually started doing research in robotics, in AI for robotics. Yeah, my first project was in visual estimation of contact, where you have an RGB image as your input, and you want to estimate where a human or a robot is making contact with its environment. And that was really the moment where I realized this stuff is quite beautiful, and it's a nice sort of elegant solution that solves, in this case, a problem that hadn't been solved in the past with even with all of the theory and physics coming before us.
Yeah, it's such a rewarding moment where you take whatever you know and you're actually useful and you produce something that people can use. It's amazing. I feel really energized and inspired, talking to you and hearing about all of this. I feel so many of us need this kind of message that you don't have to do something you don't like, and passion is something you can cultivate by showing up and using your time in an intentional manner. So I consider myself grateful for getting the chance to speak with you and learning about so much.
Thank you so much, Costa. I really, really appreciate this opportunity.